Hello and welcome to the lecture for MRI the Basics Chapter 8 for UCSF Biomedical Imaging 201. This chapter is on the spin echo pulse sequence. The distraction though for you today is this. I don't know how much I need to say about it, except that it's quite unusual for an MRI scan. This is an MRI scan of a sea lion that I came across a couple of years ago on Twitter, and just words can't describe it any more than that, I think. And then here's a few of the images of the sea lion brain. I believe this was an animal that was sick or behaving erratically, and so they wanted to look if they could learn anything from MRI of the sea lion brain. In the in-class session for this, we'll go over a couple of these different image contrasts that you see here. But they really got a state-of-the-art brain exam for this sea lion. Okay, so the learning goals for the spin echo lecture is why first are spin echo sequences used, how do they work? We're going to draw a pulse sequence diagram for the spin echo pulse sequence, and then talk about how they change image contrast. So actually, we're going to jump back a little bit here and remember the concept of T2 star relaxation. And spin echoes are fundamentally trying to address the difference between T2 and T2 star. And if you recall, T2 is this microscopic or molecular level inhomogeneities. They lead to spin-spin dephasing. And this is a fundamental, irreversible process. Now, T2 star, on the other hand, includes both T2 as well as the effects of more macro scale inhomogeneities, so on the level of our imaging voxel sizes that also lead to accelerated relaxation. And we can irreversible. We can break this up into, actually you can say that the T2 star relaxation includes the fundamental irreversible T2 relaxation plus additional relaxation, and notate this as T2 prime, where this term is our intra or within our imaging voxel dephasing. And just recall, because of this, we will always have T2 star. It's going to be shorter or equal to T2. So I want to dig into a little bit of review here of T2 star and then how this interacts with the spin echo sequence. So we go through this picture again from a couple of lectures ago. So what causes T2 star? And in this picture, we're going to look at across our imaging voxel. We're going to look at these are our net magnetizations, or specifically the transverse component of the net magnetizations, because this is what is giving us signal. And this picture is going to illustrate the fact that, well, across our imaging voxel, so maybe in different locations, we might have slightly different magnetic fields due to main magnetic field inhomogeneities, or largely one of the major factors is magnetic field susceptibility differences. And this picture is looking after excitation at, so we have some transverse magnetization, and because these different places in our imaging voxel experience slightly different magnetic fields, they're all going to have slightly different rates of rotation or rates of precession. So over some amount of time, these imperfections or differences in the magnetic field lead to this off-resonance rotation, where the net magnetizations rotate slightly differently from each other. Okay. And the effect is that over time, we get some additional dephasing decay due to this effect. So not only are these little net magnetizations here, they're shrinking in this way due to T2 decay. The sum of them across the imaging voxel is going to lead to T2 star decay. Okay, so this is repeat of that picture. Let's just annotate our different components here. It could be from different places in the voxel. And the transverse magnetization across the voxel, this is in fact our signal within a voxel, because this voxel is the smallest element of space that we can actually measure in our image. So we can't measure these individual net magnetizations I've drawn at these different locations. They're just going to be summed together in our image, and we're going to get this dephasing or from these net magnetizations pointing in different directions that lead to this accelerated decay. And we can contrast that. So we can contrast this to the case of if we had no change in the magnetic field. So if the magnetic field is perfectly equivalent across the imaging voxel as illustrated in this example, in which case all we would have is T2 decay, but none of this incoherent or dephasing averaging that leads to extra decay from T2 star. So this is where the idea of spin echo refocusing comes into play here. So again, I'm going to use this picture where we're looking at our transverse magnetizations here. And once again, we're going to assume we have slightly different resonance frequencies. And now I've color-coded them here for different locations within our imaging voxel. Okay, so we do our 90-degree flip, put our magnetization into the transverse plane. As we saw over before, we're going to, some time passes, we get this additional dephasing or rotation of our net magnetizations that depends on the magnetic field. So what we've done is we've taken these net magnetizations, they're kind of rotated. Now what we're going to do is we're going to apply a 180-degree flip angle, which is going to in effect flip these transverse magnetizations around like so. So the 180-degree flip is flipping them around, in this case, the y-axis here. Okay, so we flipped it over this way. You can think of it as like flipping a pancake, for example. And it's done for all of the spins. But now the cool thing that happens here is that each of these net magnetizations still has the same resonance frequency. They're still experiencing the same underlying magnetic field. And so they're going to continue to rotate in the same direction they were rotating before. So this is where the magic of a spin echo happens, is that, let's follow this spin on the top here. It begins oriented horizontally, it rotates up towards the top here, and it's going to continue rotating in this counterclockwise direction even after this 180. So it rotates counterclockwise, it gets flipped over, and then it continues to rotate counterclockwise. So if we choose these timings to be the same before and after this 180-degree pulse, then in fact we can cancel out completely this effect of different resonance frequencies. Let's go through the second line here, the orange. And now this net magnetization in the rotating frame is going to be moving slightly clockwise, but very slow. It gets flipped around, continues to move slightly clockwise, ends up at the exact same orientation, this horizontal orientation that it started at. And then the green on the bottom line, again, it's doing the same thing, but rotating in the opposite direction as our red top line, where it's rotating clockwise because it's at a different resonance frequency, different magnetic field. It's flipped over, but continues to rotate in this clockwise direction. And so at this very specific time, which is the same amount of time between the 90-degree pulse and the 180-degree pulse, and then the 180-degree pulse and the time we observe, is when we get this, what is called the spin echo. And we have no T2 of the extra component that was T2 star decay. We just are left with pure T2 decay. So all our spins are refocused regardless of the resonance frequency. I'm going to go through another illustration of this to solidify the concept. So this is an illustration from the book. Can now maybe do a 90-degree flip, and here we're looking at transverse magnetizations again, and following the case of 3 different resonant frequencies. Okay, and after some time, Te/2, what you can see is that spin number 3 here is moving. 3 is moving in this direction. 1 is moving in this direction, depending on their different resonance frequency. 2 is on resonance. If we continue as usual without doing a spin echo, this is what we call as a gradient echo. So no additional RF pulse, no 180-degree RF pulse. We just continue to allow the net magnetization to evolve. These net magnetizations continue to dephase from each other, and we get this shrinking that has a bunch of T2 star decay in it. But if we come in here at the middle of this picture here, and we go apply a spin echo sequence where we do a 180-degree flip. In this case, now we're going to do the flip in the across a vertical axis, so flip it left to right on the page here. And it turns out you can flip it any direction and you'll still get the spin echo phenomenon, where at this point, now you can see these set of net magnetizations are simply flipped across by the 180-degree pulse. But recall that 3 is continuing to move in a counterclockwise direction. 1 was initially moving in a clockwise. It's continuing going to move in a clockwise direction because it's still experiencing the same resonance frequency. And again, we're going to wait this equal time interval as we had between the 90 and 180 degree pulse. And we are going to get the spins here to, the net magnetizations to be perfectly aligned or in phase. And so we have eliminated the T2 prime part of T2 star. And start to draw now the pulse sequence, what this looks like. Spin echo is going to be a 90 degree pulse, followed by a 180 degree pulse, where we do an interval of TE over 2 before, and an interval of TE over 2 after. And if we look at the net magnetization at a couple of different times here, let's look right after the 90 degree pulse. So we can follow a couple of different locations in our voxel. That might assume have different resonance frequencies. Let's say a case of our orange as it was before. Was rotated in the transverse plane, and that this location is on resonance, and so it is not rotating. It's maybe experiencing some T2 decay, no dephasing effects. Our red location, say this is moving. Oops. In this picture, in sort of counterclockwise direction, the 180 degree pulse, and the way I've shown it here is a 180 degree pulse around the y axis. So this 180 degree flip is gonna flip everything 180 degrees around the y axis. And I think this drawing is a little bit easier to visualize this 180 degree flip, but it's going to continue rotating in the same direction even before and after this flip. So here, looking at these different times during the pulse sequence. And then let's suppose we have another location. It's rotating the opposite direction, so it's experiencing a slightly different magnetic field. It's going to be also rotated 180 degrees, but continue on its path of clockwise rotation. And it basically gets flipped 180 degrees also around the y-axis here. This is where this sort of pancake flip of the net magnetizations is happening. And time 4 here, this is our spin echo. So I'm going to draw this in one other way. show now. So seen the basics of the sequence a couple of times here. Let's look at where we're going to do our data acquisition, and we're going to do it centered around the spin echo time. So here's our spin echo, sometimes abbreviated SE. We're going to do our data acquisition centered around this, and you can note that the echo time from this excitation RF pulse to the center of the spin echo. And then often you'll see a spin echo drawn like this for the signal of the voxel, where 90-degree pulse creates some excitation. And now, if there was no T2 star, this would be what the signal would look like, is to have T2 decay. If there's no T2 star, our spin echo doesn't make a difference. But in the signal for our voxel, we typically are going to have some T2 star. So what that will look like is some accelerated signal decay. But what will happen at the spin echo time is actually we will recover the signal level that we would have as if we had only T2 decay. So at this spin echo point here, we're only experiencing T2 decay. Now, as is shown in the last drawing, particularly look at that picture number 5, there is still T2 star decay happening around the spin echo point. So there'll be a signal profile of the voxel that looks approximately something like this. We still have the effects of T2 star decay around our spin echo time. But right at the spin echo time, we get pure T2 contrast, pure T2 weighting at this time. And so here's another example of that, where you see this T2 star decay from the beginning of the RF pulse. And if we're just doing a gradient echo, which is a sequence on the bottom, we just have the T2 star decay. If we do a spin echo, we get to the spin echo point where we only have T2 decay. And you can see in these example images that at the short echo times, you don't see. So in the spin echo case, you can do a short echo time where we don't see too much T2 contrast, but go to a more typical long TE for the brain, where you see bright fluid, bright cerebrospinal fluid, and a typical T2 contrast in the brain. And what happens in the gradient echo is that at a much shorter echo time, in this case 25 milliseconds, we have more rapid signal decay because it's T2 star decay. And also what you notice, there's some distortions in this image, and these are the result of the T2 star phenomenon. Particularly, you got some air cavities around here from your ears. These lead to more T2 star effect, and so we actually see a signal artifact from the T2 star decay in the gradient echo images here. And this limits both the image quality and our ability to have a lot of T2 contrast. I just want to briefly show this as kind of a teaser, and because you may hear the concept of a fast spin echo or multiple spin echo, sometimes called a turbo spin echo or even rare imaging. And this is basically an extension of the spin echo where we can actually repeat this process of tipping down the net magnetization. It fans out, we flip it over, it fans back together, fans out, flip it over again, fans back together, fans out, flip it over again, and so on repeatedly. So we can actually repeatedly refocus the T2 star term and be left with pure T2 decay at multiple spin echoes. And in practice, this is practically the only way that if you spin echo sequences are used, or the majority of the way they're used, and particularly for T2 weighted imaging. The multiple spin echo sequences are very efficient, very fast, and so they're extremely powerful pulse sequence. And we'll get into these in the second half of the course when we get to chapter 19. Okay, that wraps up this lecture. So you want to review, make sure you understand, well, why are we going to use a spin echo pulse sequence? How do they work? What does the pulse sequence diagram look like? And then ultimately, how does this change the type of image contrast and in fact also artifacts that we will see? Okay, thank you for watching.